Welcome. In this video, we are going to talk through some reactions review problems so you can see some examples of the types of problems you want to be able to do. And the first type of problem you want to be able to do is to translate chemical equations into words. So if you see all these symbols down, want to make sure that you can understand what those symbols mean. And so we're going to translate those into words. So for example, on this top one right here, I would say, well, H, that stands for hydrogen. The G stands for gas, so that's hydrogen gas. Wherever you see a plus sign, I'm going to interpret that as and. And then what else do we have? We have oxygen gas. And then you could, for the arrow, there's a couple options here. You could say reacts to form, or you could say becomes, or makes, or something along those lines. So you could say hydrogen gas and oxygen gas react to make liquid water. So water is a covalent compound, and we didn't talk about how to name covalent compounds, but we're going to assume that H2O is one you're familiar with, and you know that's water. Okay, so let's try the next one. So MgCl2, this is an ionic compound. When we name ionic compounds, we first name the metal, so magnesium, and then we change the ending of the second one to "ide." So instead of chlorine, it becomes chloride, and AQ means aqueous. So aqueous magnesium chloride, and aqueous, Ag is silver, NO3, that's one of our 6 polyatomic ions we should be familiar with. So and aqueous silver nitrate forms, that's the arrow there, silver chloride. That's this one. So Ag is silver, Cl is chlorine, the ending becomes ide, so chloride, and it's a solid. And magnesium nitrate. Oh, and that one's aqueous. All right, so that's what we want to do, be able to translate chemical equations into words. And then we also want to be able to do the opposite. So here's some examples going the reverse way. So sodium is Na. It is a solid. I just realized it didn't say this in the question, but let's assume that it is a solid. Okay, plus water. And water, or state of matter of water, is going to be liquid. And then aqueous sodium hydroxide. Whenever you're writing the chemical formula for a compound, you want to consider ion charges. So the ion charges for elements you can figure out using patterns on the periodic table that we've discussed before. And then there are 6 common polyatomic ions that you should be familiar with right here. So this one is involving, what is it? Sodium hydroxide. So sodium is right here, Na with a +1 charge. Hydroxide is OH with a -1 charge. So sodium hydroxide. And then with ionic compounds, we want to consider the rule of 0, which is that the charges need to add up to 0. And in this case, +1, -1, that adds up to 0. So perfect, we are all set. We don't need to change any subscripts here. And it's aqueous, so I'm going to write AQ. And then hydrogen gas. So when something is an element, you want to ask yourself, is it part of Hofbrinkel? Okay, so Hofbrinkel is just a trick to remember these 7 elements, which we call the diatomic elements. And what that means is when it's in an elemental form, like if we have pure hydrogen, it actually is diatomic. So there's 2 atoms of hydrogen bonded together to form a molecule. Notice how sodium over here, Na, is not part of Hofbrinkel, so it is not diatomic. So I do not put a subscript there. So here's my chemical equation. This one turns out is not balanced yet, so I need to balance it. And then I think I'm all good now. There, okay. Let's look at the next one. Fluorine gas, it's an element. It is part of Hofbrinkel. So fluorine gas is diatomic, it's F2. aluminum oxide. So I'm writing this one out. It's a compound. So with compounds, I want to think about charge. So aluminum oxide, aluminum has a +3 charge, oxygen has a -2 charge. I know this from looking at my patterns on the periodic table. And so I'm going to do a little crisscross applesauce here, and that would give me Al2O3. Let me just write that below, actually. Okay, so here's F2 gas, and then Al2O3 solid will form solid aluminum fluoride. There's another compound. So if I've got a compound, I want to consider ion charges. So if remember we talked about the rule of 0. So if these charges do not add up to 0, so like +3 and -1, that does not add up to 0. That's when we want to do this crisscross method here. So if they add up to 0, then just don't use any subscripts. If they don't add up to 0, then we want to do our crisscross method here. So this becomes AlF3. It is also a solid, and then oxygen gas is part of Hofbrinkel. So that's going to be O2. And then I want to go through and balance it. So when you balance it, you end up with having a 2 and a 3. And I'm not going over the rules really for balancing here. I'm just kind of putting in the final answer. But the rule of thumb with balancing is you can, what a strategy you can use is you can make your T-chart, count how many atoms are on each side. Actually, we can do this real quick as a demo just to check that we are balanced. So if you look this one, on the left, we have 6 times 2, we have 12 fluorines on the left. Then we've got 4 times 3, we've got 12 fluorines on the right. Over on the left, we've got 2 times 2, we got 4 aluminums, and we got 4 aluminums over here. And then 2 times 3, we've got 6 oxygens over there, and then 6 oxygens over here. So now it's balanced. Woohoo! So here's an example of taking, translating these words into symbols. All right, so let's look at balancing. So we talked about balancing here. Let me do a quick overview of what the strategy would be. So you do the T-chart, and you would count how many atoms of each type are on each side. So in this case, you'd say there's 1 iron on the left, there's 2 chlorines. Over on the right, there's 1 iron and 3 chlorines. And then you want to balance these out. In this case, I see I got 2 on one side, 3 on the other side. I want to look for the lowest common multiple. So I'm going to ask myself, how can I get 2 and 3 to be the same number? What's the lowest common multiple of that? And the lowest common multiple is 6. So I want to make it so I have 6 chlorines on the left and 6 chlorines on the right. So I can do that if I put a 3 over here, that would give me 6 chlorines. And if I put a 2 over here, 2 times 3 is also 6 chlorines. It also affected my number of irons. So I need to also put a 2 right here in front of the iron. So now I'm balanced. Let's look at this next one. This is an example of something involving polyatomic ions. And if I'm doing this, I could count the nitrogens and oxygens separately, but it's often easier just to count the NO3s as one thing rather than breaking up the nitrogens and oxygens separately. So what I would say is I've got 1 copper on the left, 1 silver, and then 1 nitrate ion. And on the right, I've got 1 copper, 1 silver, and 2 nitrate ions. So to balance this out, I'm going to put a 2 over here. That'll balance out my nitrates. It will also give me an extra silver. So to balance out the silvers, I'm going to put a 2 right here. So if you haven't done this yet, try these last 2 problems right here, 7 and 8. You can pause the video for a moment and then come back and I'll show you the answers on the next screen. All right, here we go. And for these ones, when you could either write in a 1 if you'd like, or you could leave it blank. The 1 is assumed in these cases right there, just as an FYI. All right, another thing we want to be able to do is to identify the type of reaction that we're observing here. And our types of reactions are combination, decomposition, single displacement, and double displacement. And there's also combustion. I forgot to have that on the list there, combustion. So there's 5 main reaction types to be aware of. This first example, when you have element plus compound makes element plus new compound, this is a single displacement reaction. This next one, number 10, compound plus compound makes two new compounds. This is an example of a double displacement. Looking at number 11, we have two elements coming together to form a compound. That's an example of a combination. And then this last one thing's breaking apart, that is a decomposition reaction here. And then checking these bottom ones right here. This one, 13, is a single displacement. Notice how we have an element plus a compound. And then this one right here, 14, is a decomposition. I can recognize that because I just have one reactant. 15, you've got compound plus compound. Notice how the compounds are both aqueous as well. That is characteristic of a double displacement. And then this one, here's our first combustion reaction. So combustion is when you have what we call a hydrocarbon plus oxygen, and you always make CO2 and H2O as your products. I also want to point out that notice how 14 and 16 have the same products there. But 14, we do not call it a combustion, we call it decomposition, because notice how there's no reaction with oxygen here. So 14 just involves one substance breaking apart. 16, however, is a combustion reaction because it's got something plus oxygen makes CO2 and water. All right, this 17, you have two reactants, one product that looks like a combination. And then this last one is a single displacement. So you want to be familiar with the reaction types and the patterns because that will help you predict the products of a reaction. And that's what we're going to look at next here, is predicting the product. So if you mix two things together, what are you going to get? And when you predict the products of a reaction, you're either going to be writing the equation, the symbols for an element or a compound. If you're writing the formula for an element, you want to ask yourself, is this element diatomic? So if it's part of Hofbrinkel, then it's diatomic, you added 2 subscript to it. If it's not part of Hofbrinkel, leave it alone, no subscript needed. Here's an example right here. Iron oxide, when it decomposes, it will form iron and O2. Notice how Fe, it's not part of Hofbrinkel, so there's no subscript here. We just write Fe. But oxygen is part of Hofbrinkel. That means it's diatomic, which means it comes in pairs. So oxygen gas is O2. And then, so if we're not writing an element, we're going to be writing a compound, and we're only going to deal with ionic compounds. I should say, we might also see water and CO2. Those are the really the only covalent compounds we might run into. But otherwise, we're only predicting products of ionic compounds. So when you have a metal and a non-metal. And when you're writing the formula for ionic compound, you want to consider charge. So you write down the ion charges of the elements that are combining, see if those charges add up to 0. If not, do the crisscross method to determine the subscripts of the formula there. All right, so let's give this a try. These ones are all combination and decomposition reactions. And if you haven't tried these reactions yet, then you should hit pause right now and try these on your own. And then you can hit play again and check your work. All right, so if we take a look at these ones, 19 and 21 both look like combination reactions, where you have two elements coming together to form a compound. And when you're writing the formula for a compound, we just said what you want to look at is the ion charges. So we're mixing together aluminum and fluorine. And then we look on a periodic table and we say, okay, aluminum has a +3 charge, fluorine has a -1 charge. These charges do not add up to 0. So what I need to do is do my little crisscross method here, and that gives me AlF3. Okay, so this is my product. Notice how the subscripts over here are not the same as the subscripts over here. So the way you figure out the subscripts is not by looking at the reactants, it's by looking at the charges of your ions. That's how you determine the formula of your product. And then if you find the subscripts don't match, you might need to go through later with coefficients to balance it out. So in this case, I need a 3 over here and a 2 over here. That will give me 6 fluorines on the left and 6 fluorines on the right. And then I also will need a 2 over here. All right, let's take a look at this 21, the other combination one. This time we're combining lithium and chloride. And if you look on a periodic table, lithium has a +1 charge, chloride has a -1 charge. So they add up to 0. So no subscripts needed here, because +1 and -1 add up to 0. That's our goal, is to get these charges to add up to 0. So this compound is just LiCl. Notice how I start with Cl2 and I end up with only 1 Cl over here. So I need to put a coefficient out in front. Now I've got 2 chlorines, 2 chlorines. I also need to balance out my lithium. If you want to, you could throw a 1 out here. That's our balanced equation here. All right, and then these other two are decomposition reactions, so they're going to break down into elements. So when we're writing them as elements, ask yourself, is it part of Hofbrinkel? So nickel bromide is made up of nickel, which is Ni, and Br. So I'm going to go and I'm going to look at Hofbrinkel. And if something's part of Hofbrinkel, like Br, you give it a 2. If it's not, like nickel is not part of Hofbrinkel, then you just leave it as Ni. No subscripts are needed there. And then we go through and we balance it. So if I put a 2 over here, and a 3 over here, and a 2 over here, everything gets balanced. And all right, let's try another one. I've got AlF3, so it's going to split apart into elements. Whenever we're writing the formula for elements, ask yourself, is it part of Hofbrinkel? So aluminum, not part of Hofbrinkel, so no subscript. Fluorine, yep, part of Hofbrinkel. So what that means is it's diatomic. I'm going to give it a 2. Fluorine comes in pairs. Okay. And then once again, notice my subscript on the left does not match the right. So that means I need to go through and I'm going to need to balance things out using coefficients. So I got another example where I got 2 and 3. What's the lowest common multiple? 6. So if I put a 2 over here, now I got 6 fluorines on the left. Put a 3 over here, I got 6 on the right. And then I put a 2 over here. All right. And I am kind of quickly going through the balancing piece of it because this is something that we covered in an earlier topic, but let me know if you have questions on balancing and I can help you out there. So let's talk about the last type of reaction. So notice how these ones were combination and decomposition. We're going to take a look at some single and double displacement reactions. And these are some reactions that involve aqueous systems, which basically means that these are reactions that tend to occur in the presence of water. You tend to mix a solution with something that's a solid, or you mix 2 solutions together. And so it's important for us to consider, when we're looking at these types of reactions, whether or not a substance will dissolve. So we want to use these solubility rules to figure out whether or not a substance will dissolve in water. And the way you use this table is you kind of look and match things up. So like if something involves lithium and nitrate, you see an S right there. S means soluble, means it dissolves in water. And something that's important to notice that the entire row with nitrate and the entire column with the alkali metals, lithium, sodium, potassium, these are always soluble. So if you see NO3 in a compound, just assume soluble. Same thing, if you see Na, it's always going to be soluble, no matter what. So these rules are kind of useful to just remember. These two are always soluble. But you can always refer back to this table to figure out who's soluble and who's not. All right. And then remember, when you're writing out the formulas for compounds, you're going to want to know the charges of the elements using this table, and then the charges of the polyatomic ions. All right, so these is going to be a combination of single displacement and double displacement reactions. And in both cases, the simplest way of thinking of it might be to think of the metals switching places with metals, or non-metals switching places with non-metals. Okay, so let's look over here. So we got magnesium as a metal. So in a single displacement, look at the identity of the element on itself. by itself. And if the element by itself is a metal, it's going to switch places with the metal. And the way that we figure out metal versus non-metal is these ones over here on the left, these are all metals. So notice that like a magnesium and who else was it? Copper. Okay, those are both metals. They're going to switch places with each other. All right, so the copper is going to go by itself, and then the magnesium is going to go with the nitrate. Whenever we're writing an element, ask yourself, is it part of Hofbrinkel? Copper is not, so copper just stays Cu. And if you're wondering what's the state of matter, you can copper something we've seen before. You're probably familiar with what copper looks like. It is a solid at room temperature. And then when you're writing a formula for a compound, you want to consider charge. So magnesium is +2, nitrate has a -1 charge. How do I know that? Well, I've got my reference right here to figure out my charges over here. And they do not add up to 0, so I need to do a little crisscross, and my formula is MgNO3 2. And using my solubility rules, we saw that any compound containing a nitrate is going to be soluble. So if I combine magnesium and nitrate, that's soluble. So what that means is that this substance is going to dissolve in water. It's AQ. All right, let's try another one. So aluminum is a metal, so it's going to switch places with the metal in this compound. So that's how single displacement reactions work. The metal switches places with the metal. And so now, again, we form solid copper. And then the aluminum now combines with the chloride. Okay, and again, notice I didn't write Cl2 because now it's not by itself anymore. It's part of a compound. So to figure out the subscript, I have to look at ion charges. So if I look back here, I see that aluminum is +3, chlorine's -1. All right, those charges do not add up to 0, so I need to do a little crisscross. So it's AlCl3. And if I want to figure out the state of matter of this, I can go back here and look at my chlorides. And I've got chlorides and actually aluminum's not on here. Chlorides are mainly soluble unless they're combined with silver, lead, or mercury. I just realized aluminum's not on my table though. Okay, we can assume aluminum chloride is soluble. All right, so this one will also be AQ. So I'll try and avoid one like this on a test or quiz here. And if I want to balance this out now, I want to put a 3 over here, a 2 over here, and then a 3 and a 2. So that's my balanced chemical equation. Here's another single displacement. In this case, though, chlorine is a non-metal, so it's going to switch places with the other non-metal. And again, how do I know this? If I look back at my periodic table, chlorine's over here, so is bromine. So they're gonna switch places with each other. And all right, so the bromine is now going to be by itself. And whenever you write the formula for an element, ask yourself, is it part of Hofbrinkel? In this case, yes, it is. So it's Br2. Okay. And then the sodium is going to combine with the chloride, and +1 charge, -1 charge, no subscripts needed. Okay, so cool. And sodium chloride, that is table salt. So is it soluble? This is something you might have personal experience with. Yes, in fact, it does dissolve in water. And if you look at your solubility rules, any sodium compound is going to be soluble. So because it contains a sodium ion, it will be aqueous. And then we'll go balance it. All right. And then now we're getting into some double displacement ones. So in this case, you can also think of as the metal switches places with the metal. Another way to think of it is the positive ion switches places with the other positive ion. So our products here is your calcium combines with your phosphate, and then your sodium combines with your nitrate. So I just wrote down what the pairings are going to be. Now I have to look at charges to figure out the formula. So calcium is +2, phosphate's -3. They do not add up to 0, so you can do a little crisscross here. So that's going to be Ca3PO4 2. And then we go back and erase the charges. That was just a little note to myself there. And then sodium is +1, nitrate is -1. So in this case, they do add up to 0. So no subscripts needed. And then if I want to figure out these states of matter, we said before that any compound containing NO3 is always going to be soluble. So that's AQ. And then over here, calcium phosphate. If we're not sure about that one, let's go check. Phosphate compounds are typically not soluble. So calcium plus phosphate, that is in the not soluble area there. So if it's not soluble, that means that it will not dissolve, which means it will be a solid. So we will see a solid form when we mix these two solutions together. Then we've got to balance it. So I'm going to put 2, and 6, and a 3. All right. Let's look at one more set here. So with these ones, I encourage you just to hit pause and try these if you haven't yet. With this one, with number 27, we want to assume that copper is going to, copper will have a +2 charge. I'll put that little note there for you. And then the other one that's kind of odd, actually down here with 29, is you might look at this compound on the left and say, well, there is no metal, right? We said that ionic compounds are a metal and a non-metal, but this one doesn't have any metals. It's all non-metals. So what this is NH4. We flip back here. This is the one example of what we call a polyatomic ion that has a positive charge. And you know who else has positive charges? Is metals. So ammonium will kind of behave like a metal in this type of reaction because it's just a positively charged ions. And really what's happening is the positively charged ions are switching places with each other. So in this case, the NH4 and the silver will switch places. So pause the video and try these. And then when we come back, you can check your work. All right, so now that you have taken a minute to try these ones, I'm going to show the answers so you can check your work. So here we go. So this first one was a single displacement reaction where the silver and copper switched places. And then 28 was a double displacement. The magnesium and the sodium switched places. The magnesium hydroxide is a solid. Sodium chloride is soluble, so it's AQ. In this case, the NH4 and the Ag switch places, so you form ammonium nitrate, which is soluble, and then silver bromide, which is not. And then here, the cobalt and the potassium switch places, cobalt hydroxide and potassium chloride. And again, remember, whenever you are predicting products, if you have an element by itself, like in the case of silver, just ask yourself, is it part of Hofbrinkel? If it is, give it a subscript 2. If it's not, then just leave it as the symbol. Okay. And then when you're whenever you're writing formulas for compounds, consider the ion charges and make sure that they add up to 0. And that might involve some crisscrossing to make that happen. All right, so that's it. Thanks for watching, and send me a message if you have any further questions.